All right, the next thing we're going to talk about today is periodic table trends. So there are three things, three properties that atoms have that you can look at the periodic table and see where an element is on the periodic table and determine where it's going to fall on this scale of these three properties. Okay, so the first one is atomic radius. And just like it sounds, it is the size of the atom, the distance from the center of the nucleus out to the farthest away electron orbital. So it's just how much space does one atom take up. All right, atoms with more electrons need more orbitals, right? If you start adding more electrons, once you get past 2, you got to go out to that second orbital. Once you get past 10 total, you go out to the third orbital. Once you get past 18 total electrons, you got to go out to fourth orbitals, and then you just get more and more as you go. So the atoms with more electrons, so the larger atoms, the higher atomic number ones, have more orbitals, so that makes them bigger. They have larger atomic radii. Right. The other thing that affects atomic radii is that opposite charges attract. So like when you've got a magnet and you have the north pole and the south pole of two magnets, they'll stick together. If you've got two north poles, they push each other apart. In the atom, the protons are positively charged, the electrons are negatively charged, so they're opposites, and they want to get close to each other. They attract each other. So what happens is the protons in the nucleus pull the electrons in close to them. It scrunches everything down. So atoms with more protons that have the same number of orbitals are going to be smaller than atoms with fewer protons with that number of orbitals. So if we look here, what that means is that overall atomic radius is going to increase as we go down and to the left. All right, that's what it says. This is a typo. I'll fix that. Down and to the left, it gets bigger. So say we're just looking at this row here that starts with potassium, the K. So these have 1, 2, 3, 4 orbitals total. So they're all going to be in that same category of having 4 orbitals in this row. But krypton over here has way more protons than the potassium does. So those extra protons pull the electrons in and hold them there. All right. So they're going to be smaller on this side than they are over here. And that's kind of what this chart is showing. If we look here, we've got helium is our very first one. And then hydrogen, it has 1 extra proton, still has only the 1 little orbital. So that 1 extra proton pulls the atoms in a little more, and it has a smaller atomic radius. It goes down a bit. Then we go to lithium, the next one, and it jumps up. That's because we're adding a whole new orbital. So lithium, beryllium, all the way through neon, they all have 2 orbitals. And as you can see, as we go across the periodic table and get more and more protons, the atomic number going up, the atomic radius shrinks down. When we get to neon and then go to sodium, Na, from here to here, it jumps up again because we're adding another orbital. All right, you guys get the picture. So the main thing, atomic radius increases as we go down and to the left. Biggest atoms over here is francium. Smallest atom over here is helium. All right, the next thing is electronegativity. So basically what electronegativity means is how likely an atom is to take an electron away from another atom. So how likely it is to go out, grab some other atom's electron, and take it for itself. All right, and the most important factor here is the number of valence electrons the atom already has. We kind of talked about this yesterday during the valence electron lesson, but when we're looking at, let me go back to the periodic table here. When we're looking at these halogens over here in the 7th, or in the row that has 7 valence electrons, they only need 1 more to have their full outer shell. They want 8, they have 7. So if they only need 1 more, they're going to do whatever it takes to go out and grab that 1 electron from someone, right? So the more valence electrons they have, the higher their electronegativity is. All right, so over here in the alkali metals column, all these guys only have one valence electron. In order to get their outer shell, if they were going to take electrons away from people, they would have to go out and get 7 electrons to fill up to 8. And that's a lot of work, right? They would rather just give that one away and go down to the next shell below. So their electronegativity, their likeliness to go out and get electrons from other people, is very low. Right? Another factor that affects this is that the closer the outer shell is to the nucleus, the more pull the protons have on other electrons. So what that means is if you've got an atom that has 8 orbitals on it, and your 8th orbital is 1 electron shy, yeah, it wants that extra electron, but that 8th orbital is so far out away from the nucleus, way out in space, that the nucleus doesn't have as much power to reach all the way out there to another atom and grab something and put it in that 8th orbital. If we're talking about one of our smaller atoms like fluorine, its shell that it wants to fill up it's only the 2nd shell, right? So it's much, much closer to the nucleus, and the protons pull, that opposites attract pull that we were talking about with atomic radius, is much stronger when it's closer. So what this means is electronegativity increases as we go to the right, because more valence electrons means more electronegativity, and it increases as we go up the periodic table because the smaller atoms have more pull to them. All right? So the exception to that rule is that the noble gases, the very last column on the right, they already have full outer shells. They have all the valence electrons they want. They don't have any interest in going to get new ones, so their electronegativity is 0. So we can see that here. If we're looking at the chart, from helium, it's got relatively high electronegativity. It wants just 1 valence electron to fill its outer shell, because that outer shell for helium only needs 2 to be full. And it's as close to the nucleus as you can get. It's that very first orbital. So it has relatively high electronegativity. And then we go over to helium, which is, I've blacked out this column for the graphic here, but helium's right here. And it's got 0 electronegativity. It's got a full outer shell. Doesn't care. Doesn't want any more electrons. And then as we go our next row, as we go across it, we slowly go up, all the way until we get to fluorine, which has the highest electronegativity out of any element because it, like we said, it has 7 valence electrons. It just wants 1 more. And that outer ring that it's trying to fill up is very close to the nucleus. All right, and then we go to the next one, which is right here, neon, and it's bloop, straight back down to 0. Next row is the same story. It goes up until we get to chlorine. And then we get to argon, the next noble gas, and then straight back down to 0. All right, so that's kind of the story of electronegativity. You can see there's a little bit of funky stuff going on here in the transition metals, but don't worry about that. The general rule is that as we go up and to the right, we get more electronegativity, with the exception of the noble gases, who all have electronegativity of 0. All right, and the last one, the third one, is ionization energy. So this is how much energy it takes to remove an electron from an atom and turn it into a cation. If you remember from last time, a cation is a positive ion, which makes sense if you're taking away an electron from it. The electrons are negative charges, so if you remove one of those, overall you're going to have a positive ion left over. All right, so ionization energy is how much energy it takes to do that, to take away an electron. And this is kind of similar to electronegativity. Atoms that are close to having a full outer shell, if you try and take away those electrons from them, they're not going to want to let you do it. They want to hold on to those as much as they can, because if you take it away, it just makes more work for them to fill their outer shell up. All right. Similarly, if we're looking over here at the atoms with just 1 or 2 valence electrons, they don't care if you take it away. That's helping them out, right? So it doesn't take very much energy at all for you to take away a electron from one of these guys over here. It's happy to give it up. All right, and then kind of the same story with the size of the atoms. The smaller atoms, those valence electrons in that outer ring, are close to the nucleus, so there's more attraction there, so it's harder to pull the atoms away. All right, the larger ones, the farther out you get away from the nucleus, the less pull those protons have, and it's easier to yank something away from them. So the general trend here is that, again, it's going to increase as we go up and to the right. So very high ionization energies takes a lot of energy to break an electron off over here, and very low ionization energies over here. All right, and this time the noble gases, they do follow the trend. They actually have the highest ionization energies, because if you think about it, they're happy the way they are. Why would they let someone come in and take an electron away from them? So they're going to hold on to those as tight as they can. So you can see that in the graph here. As we go up, generally it gets higher and higher and higher, and then the noble gas is the highest in each row, and then it falls back down real quick to, to sodium, or to the next alkali metal, where they have very low ionization energies, and they're very willing to give up their electrons. Okay, so that's the trends of the periodic table. You guys have an assignment for this one. That is a Google Doc that I want you to download and fill out and submit, and then you'll be done for the day.